Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you to the lecture number 9 for the course of Microprocessor Theory and Interfacing. My name is Engineer Jafar Ali and I am your instructor for this course. So I've told you that this is our lecture number 9 and the topic of today's lecture will be interfacing of microprocessors, that how you can interface microprocessor. So we'll start with the term interfacing, and later on in the lecture we will discuss about the interfacing of the microprocessor. So today's our lecture outline will be something like that. We will start with the discussion of the memory, as we know that we have already discussed the types of memory in the previous lectures as well, but keeping that in mind, we will now follow towards the interfacing of that memory with the microprocessor, that how you can interface that memory with the microprocessor. So the next thing that we are going to learn today is the structure of memory and how what are the requirements for this memory structure. And the main theme of this lecture will be the third part, that is how you can interface the RAM and ROM with the 8086 microprocessor in the minimum and maximum modes. We will discuss both the modes, in the interfacing of both the modes. And in the last of the lecture we will discuss different types of address decoding. You will learn these topics in today's lecture, inshallah. So let's start with the introduction, that what is memory. So memory is basically a simple device that is used to store some information, and you know that this information is stored in a form of bits. And we have already discussed that how you can store this information using registers, and in the register there are buffers, which are basically temporary locations to store some bits. Only one bit is stored in one buffer, and the combination of buffers is termed as registers, and the combination of registers is termed as the register banks. So the semiconductor memories are used extensively because of their small size, the low cost, their high speed, their high reliability, and the ease of expansion, or you can say the upgradation in the future. You know that in the advancement and the growth of these semiconductor devices have led to a universe that there is a competition in the field of memory. In the previous times they were in the enough memory of 128 MB was enough, and later on you know that nowadays it is not possible for anyone to have a RAM of 128 MB or 512 MB, even 1 GB RAM. So this is because of the size of and the speed of the devices and their performances. So it consists of mainly the flip-flops and the other relevant and additional circuitry such as buffers, and you also know about the crystal oscillators and some supporting devices as well. And one flip-flop can only hold one bit of data, and this data is basically stored in one buffer. And we have already discussed that this flip-flop is normally the D flip-flop. So let's talk about the basic fundamentals of the memory. So the basic thing, or the basic fundamental, is one of those fundamentals is the memory capacity. And what is capacity? By capacity I means that the number of bits that are required by a semiconductor memory chip can store in itself. That is basically known as the chip capacity. So the larger the size of the chip, the greater the size of the memory, and vice versa. The next thing about the next fundamental of the memory is basically the organization, that how this memory is organized. You know about they are one type of device that is basically SSD, and the other one is that you normally use of the hard disk. And you know that SSD is more costly as compared to the other memory, and so also there are different types of memories that are involved. We have discussed the different types of memories, and we will also have a brief overlook over that in today's lecture also. So each memory chip contains, let's say, 2 power n locations, whereas there is the number of address pins of the chip. So that depends on the how many address pins you actually use. If you are using only one pin, so you can have 2 power 1 locations, that means 2 locations of memory. But if you are using, let's say, 3 pins, so you can have 2 power 3 locations as a whole. And each location contains m bit, where m is the number of data pins on the chip, and the entire chip will contain 2 power n multiplied by m bits. So for example, let's say you have a memory of 4 kilo, and the locations that are possible locations is basically turned out to be 4k multiplied by 4, or you can say 2 power 12. These is basically 4096 location, 4096 location, and each location is holding basically 4 bits. So n is equal to 12 and m is equal to 4. Now this is the topic that we have already discussed in the midterm, and you know that there are different types of memories that are used in a device or microprocessor for your interfacing purposes. The first one is ROM, that is read-only memory. The second one is PROM, that is programmable read-only memory. The third one is EPROM, that is erasable programmable memory, in which you can erase the programmable memory. And the fourth one is basically EEPROM, that is electrically erasable. In this kind of ROM, you have to provide some electrical signal to erase the memory or the data stored on the memory. And the second last one is the flash memory, or you can commonly known as EPROM. And the last one is RAM, that is random access memory. And you know that there are 2 types of RAM. The first one is SRAM, that is static RAM, and the second one is DRAM, that is dynamic RAM. And in SRAM, there are storage cells involved that are made up of double F, or you can say in DRAM you can use MOS, that is metal oxide semiconductor devices or capacitors to store a bit. SRAM basically does not require to get refreshed after some time, but in dynamic RAM you have to periodic refresh your data or your memory to keep your data on the device, on the memory, because of the leakage malfunction. You know that in DRAM there is a malfunction that is known as leakage, so that is why you have to have the need of the periodic refreshing. In SRAM, a cell handling is basically requires 6 to 4 bits, 6 to 4 transistors each, which is too many, and the density of DRAM is actually high. And let's talk about the cost. So DRAM is basically cheaper as compared to the DRAM when you're talking about per bit cost. And in SRAM, this SRAM is basically used for cache memory and battery backup memory system. And the last the point of DRAM is basically there is a large power consumption of DRAM, actually lower power consumption and larger access time. So you know that the larger the access time, the more delay. So the dynamic RAM, there is a more delay as compared to the static RAM, because there is different types of malfunctions involved in it. And the last point of DRAM is that there are too many pins, due to which the capacity can be you can increase the capacity of the memory. So this is the example of a standard EPROM IC. There are several ICs, but this is a standard IC. You can see that there are different types of ICs involved in it, and these ICs are basically providing you different types of capacity. For example, 2176 provide you a density of 16K. That means 2K multiplied by 68. This means 16K. So similarly, this 2K, this 2 provides you 32K. This 227C 64. This 64 means this is providing you a density of 64K bits, or the capacity will be 8K multiplied by 8. And similarly, this is for 256, this is for 512, this is for 1 MB, this is for 2 MB, and this is for 4 MB. And it may be possible that nowadays there is a kind of EPROM which is basically more than this 4 MB, So do not need to worry. This is basically a EEPROM standard IC. This is basically the SRAM standard IC. You can see that this is basically 4361, 4363, 4364, 43254, 43256A, and 431,000A. This is basically different standards ICs for the SRAMs, and these are the different density aligned with it, and the memory organization will be something like this. The standard DRAM IC is basically you can see that there are different ICs that provides you the dynamic RAM basically is the type of EEPROM, and in also this you can see that this different ICs are providing different types of capacities and different type of density in the form of bits. So let's talk about the memory structure, that how you can what are the requirements and what is the structure of the memory. So you can see that there is some inputs from the, you can see that there are some inputs. Let me highlight it for you. There are some inputs. These are the inputs, and this is basically input buffer. So the data that will be entered by the user will be stored temporarily in this buffer, and this decoder will be helping the user or the machine to collect the data of their requirements. Not all the data will be needed, only the decoder will choose that what data it requires. And after the processing over here, read-write memory, the output will be stored in this, and this will be termed as the output buffer. This is the output buffer in which the output will be stored temporarily, and you can also connect some read bits or write bits over here. You can see that read bits are connected with the output buffer, and the write bit are connected with the input buffer. You can edit the input, but you can take the output or you can read the output from here. So this is basically a read-write memory of this data or this memory, and this is basically the EEPROM memory. You can see that this is the random access memory, but read-only memory, but erasable and programmable. So you can see that this is a slight different. Instead of this input buffer, there is no input buffer over here. You can see that there is no input buffer over here. So this is the small difference between the read-write memory and the EEPROM memory. So now let's talk about the physical structure, and this physical structure depends on certain things. And the first thing is basically the address pins. So you know that as the number of the address pins gets more and more, you can basically increase your memory locations, and by memory locations you are trying to increase the other phenomena, that is the memory capacity. So the more memory locations, the more capacity that you have. If you are using just 8 bits, it means you can have a total of 2 power 8 locations, that is 256 locations. If you are using 9 pins for the address pins as address pins, you can have the locations, possible locations can be 2 power 9, or you can say 512. Similarly, if you have 10 pins of usage for the address pins, you can have 2 power 10, and similarly the list goes on. For this case, let's say 2 power 90, the total locations, number of possible locations can be 2 power 19, and the total memory locations will be 512k, and for this you will be having 2 power 20 memory locations, that is 1 MB of locations. The second thing that basically is represents the structure of a memory is basically the data pins. That where is what pins are allocated as a data pin. So number of flip-flops in each location can be 4 or 8. So the data pins will be 4 or 8. So it depends on the number of flip-flop in each location. If you can see that these are the possible locations, and the number of flip-flops in each location is basically termed as the data pins. Control pins are those pins which are basically there to control the memory. So you know that this read and write operations that we have discussed, this is basically the control. This WR and this RD are basically the control pins. And the last thing is common pins, or you can say chip select. This is CS, or you can say that chip select. and this chip select is used to generate some kind of signal, and this is generated using the NAND gate. You can generate a signal using NAND gate or 3 to 8 decoder or PAL IC. This is the IC that is used to generate this CS, or you can say chip select, that what chip you want to select. So for chip selection you can use these three methods as per your requirement. So let's talk about something that is known as address decoding. And in general, all the address lines that are not used by the memory locations or memory devices to select a particular memory locations. So the remaining lines are used to generate the chip select, or you can say the CS. I've already told you about the CS. So the important thing is that, let's say if you have 10 lines as input pins, 10 input pins, but you want to access, let's say there are 5 input pins. Let's say, to make it very easier, these are 5 pins: 1 2 3 4, this is 3, this is 4, and this is 5. These are the 5 pins, and we want to access let's say the memory bit of 10. It means you want to access 2. So you know that to access 2 you will be only needing only 2 lines, these 2 address lines. So these 3 lines will be get wasted. So to overcome this kind of deficiency, these remaining lines will be used as a method, or you can say use as a alternative to generate the chip select logic. The CS logic will be used. The CS chip select logic will be generated using these 3 lines. And there are 2 kinds of techniques that are used to decode these addresses. The first one is absolute or full decoding. The second one is linear or partial decoding. We will talk about the absolute decoding in the with examples in today's class, and in the coming lecture we will discuss about the remaining part, that is the linear or partial decoding. So let's talk about what is address or absolute or full decoding. So you know that all the higher addresses lines are decoded basically to select the memory chip. If you want to select a chip, you have to provide all the higher address lines. There is a need of the higher address lines to be decoded to be very first, and the memory chip is then selected only for the specified logic levels on these higher level orders of address lines. As I've already told you in these examples, that if you have to select this memory location, you go for the higher address lines, not with the lower. So you have to go from the higher, and if you have done this, the remaining lower lines will be used as the method to select your chip select logic. So each location have a fixed address, and this technique is quite expensive as compared to a partial or a full you can say partial or linear decoding, and it needs more hardware as compared to partial decoding. So these are 2 you can say limitations of this absolute decoding, but let's go with an example so that you can have a better idea about what is this thing. But before that, let's talk about briefly about this partial decoding. This technique is used in very small systems. So if you have a small system, this decoding technique is very much good for you, because it has a lot of advantages over full decoding or absolute decoding. So this is more compatible with the small systems. All the address lines are not used to generate the chip select logic. You can have individual high order address lines, and that address lines will be used to decode the chip select for the memory chips. You can see that this is the reverse of this thing. You can actually select these higher lines for the chip select logic, and in this kind of decoding, the hardware required will be less, and the only drawback is that the address of the location is not fixed. So it is possible that for each location you can have multiple address. For example, the first time you check a data, it was stored in this memory, in this location of the memory, and second time you check, this data will be shifted towards here. So this is the only drawback that is with the partial decoding. Other than this is very much that is why that is the reason that for that it is used in small system, because if you have a small system, it will be easy for you to locate the data within the location of a memory. If you have a large memory, you can understand that it will be a very tidy job to find this kind of data that will be shifted in the large location. So that is why this partial decoding is mostly suitable in the small system. So let's talk about an example of the full or absolute decoding. We have asked you that you have to interface the 32 kilobyte of RAM memory with the 8086 microprocessor by using absolute decoding with suitable address. So the first thing that you need, the first step that you have to take is basically to find the total RAM memory. So it is given that the total memory is actually 32 kilobyte, and you know that the half of this memory will be 16 kilobytes. So the number of ICs that you will be requiring will be 2 ICs, and these ICs will be of each of 16 bits. So you know that the first even bank will be of 1 IC of 16 kilobyte, and the odd bank will be of 1 IC of 16 kilobyte of RAM. Both of these will be combined to form the total RAM memory of 32 kilobyte. The second thing is that you have to specify the address lines. So the address lines you will need in this kind of circuitry provided by the examiner, or the question it is asking the question to provide a suitable address. So for that you have to find the first thing, that is the second thing, that is the number of address lines, and it has turned out to be 15 address lines. And you can see that from A0 to A19 there are this 20 bits of register, in which this from 15 to 19, these 1 2 3 4 5, these 5 are basically reserved for the decoder, and this is from 0 to 14. This 15 is basically the memory locations. So this 15 is basically this 15 lines from A0 to A14. This is basically the 15 address lines. And the third step is basically you have to draw this address decoding table, and you can draw this by using this information. So this is your memory IC, this is the hexa address, and this is the all the bits are 0, and this is basically your RAM, 16 cross 8 RAM, and this is the first one. You can see the even or the odd. We have already taken one. And the last thing is you have to the remaining lines. I have told you that the remaining lines, these lines will be used from these lines. These lines will be used to generate the chip select logic. So you see that this A15 to A19, this will be used to generate for the generation of chip select logic. So these lines will be used as CS logic generator. This thing is enough. This is just for your explanation, and this diagram will be explained to you in the notes as well. I will be providing. I have already uploaded. I will upload this notes with the lecture as well. So you will be seeing this diagram in the notes as well. So for this diagram you can take help from there, but there is no use for this example over here. But just for the relevancy and the correlation, I have provided this complete diagram to you. The second question is that we have to interface the 2 bit of memory to 8086 microprocessor but the memory chips that are available is basically 16K and 16K multiplied by 8 RAM. So you have to use a suitable decoder for the generating for the generation of chip select logic as well. So you know that the total memory available is 32K, and it is given that it is basically 16 cross 8. So the total memory will be 32K. The ICs available in the market will be of 16K, let's say. So you will be requiring the number of RAM ICs required will be 64K. That is the total memory divided by multiplied by 8 divided by 16 multiplied by 8. So the total number of ICs will be 4, because this 8 will be cancelled out with this 8, and the total number of ICs that you will be requiring will be 4. So these will 4 ICs will be required for this kind of question for interfacing. So it means that you will be needing 2 ICs for the even bank and 2 ICs for the odd bank. 2 ICs of 16K multiplied by 8 and 2 ICs of 16K multiplied by 8 for the even and odd respectively. And the second thing is that the number of the second step, that is basically we have to find the number of address lines required. So this is basically the same, that is 15 address lines. And how we can get that? By using this address decoding table. You can see that from A0 to A14 the same is given for this 16K IC, and the remaining will be given to the decoder. And you know that there are these 2 RAMs involved for each of the even and odd. So you can see that let's say this is odd, so you can say this is odd 1 and 3, this is odd, and this decoder lines, that is from A15 to A19, will be used to generate the chip logic sequence, or you can say CS generation, and the remaining will be used as the address lines. So you can see that this because this is 3 cross 8 decoder, this IC is basically 3 cross 8 decoder. So the input will be these 3 and the output will be this 8. You can see that 1 2 3 4 5 6 7 and 8. So this, because this is this 3 cross 8 decoders, so the remaining last these two will be used for the chip selection logic, A18 and A19, and these 3 will be not taken as the decoder, because as a CS generator, because this is used for the decoding purposes. And the remaining, if we, let's say this will be, let's say for instead of 3.3 ratio 8, it will be 4 ratio 8. So this A18 will be here, and only one A19 will be used for the generation of chip select logic. So this was all about the address decoding. I hope that you have learned very much in this class, and I look forward to seeing the class, and please bring some good questions along with you, because you know that the more you ask, the more you learn. Thank you very much. I'll see you in the class. Allah Hafiz.